Hello everyone. If you're watching this, I'm at the zoo, but I still have to teach y'all about kinetic molecular theory, though I think you pretty much already know what it is. So pretty much what it says is that the total amount of energy in your gas, so they call that U, it's like they call it internal energy, it's kinetic energy because like the gas is moving, is directly proportional to the temperature. So U is going to be like internal energy, it's kinetic energy. And this alpha is proportional to. And this big T is temperature. And just to be safe, anytime you use temperature, we're going to use in Kelvin. Okay, so if I pull up the simulation for the gas, and we're going to look at the kinetic energy graph on the bottom left of the screen. So it's in green. So this is for a light particle at 300 Kelvin. And then if we compare the kinetic energy graph for the heavy particle, also at 300 Kelvin, it's exactly the same. Because if they're at the same temperature, they have the same average kinetic energy. So temperature is going to be a measure of average kinetic energy. So temperature is average kinetic energy. And you'll figure this out when you played around with the ideal gas simulation. If you increase the temperature, you increase the kinetic energy. So in general, you will make the particles move faster. So temperature is related to speed, right? Because if you increase the temperature, it goes faster, but it's really average kinetic energy. So if you remember the formula for kinetic energy, but even though you don't have to, it's in the formula chart, kinetic energy is 1/2 mv squared. So if we were to compare like the speed graph for the light particle and the heavy particle, so that's going to be the white graph on the left-hand side. So the heavy particle, the speed graph looks like this. For the light particle, the speed graph looks like this. So since they're at the same kinetic energy, because they're at the same temperature, the smaller one, in order to compensate for being smaller, right, because it has a smaller mass, its velocity has to be bigger. So it can have the same kinetic energy as the heavier one. Or if you want to look at it the other way, since the heavy one has a bigger mass, it has to have a smaller velocity, so it can have the same average kinetic energy as the light gas. So when we compare the heavy gas and the light gas at the same temperature, the kinetic energies can be the same, because if they're at the same temperature, they have the same average kinetic energy, but the speeds are going to be different. The lighter one is going to be faster, the heavy one is going to be slower. So if we were to look at the formulas for like total internal energy, let me pull the formula chart. They're going to be like on the second page. So this is the first page, first semester, and the second page, second semester. It's going to be right here. So it's really the bottom three, but I'll just copy everything. Copy. So whenever you're solving some of the problems in your homework, you are going to use these formulas right here. So let's start with the one in the middle. So the one in the middle, it's like 1/2 mv squared, but there's a little bar over v. So the little bar means like average. So you're going to use, or really means per mole. So this one will tell you like the kinetic energy for like a single molecule. So energy, it's an N, for like one single gas particle, one. And that's going to be equal to 3/2. And this Kb is Boltzmann constant. That is this Kb. You don't have to memorize what it is. You just have to know when to use it. But if you're curious to where it comes from, it is equal to this R that we've used in the past and that you use in chemistry divided by Avogadro's number. So this is the Boltzmann constant. Boltz. I can't spell his name. I think it's 2 N's. Boltzmann constant. And this big T is temperature. But again, you have to make sure your temperature is in Kelvin. So just be safe, anytime you use temperature, it's in Kelvin. so you're gonna use the middle one if you're asked to find the energy for like one single particle of gas. If you want to find the energy for like the total amount of gas, you're going to use the third one, where U is the total amount of energy, N is the number of moles. Oops. This big R is the same big R we've been using, and this T is in temperature, but again, you have to make sure your temperature is in Kelvin. So you're going to use the third one whenever you're asked to find the energy, like the total energy of the gas. But sometimes it's unfortunate if you're not given an RT. That kind of sucks, but it's okay because we have another equation that tells us what N times R times T is equal to, and that's equal to pressure times volume. So if you want, sometimes you can make another substitution. So the total amount of energy U is equal to 3/2 times the pressure of the gas times the volume of the gas. So this third one, or I guess the first one, the one I'm talking about, the first one, I don't think I've ever seen this be used, but it's there. So it's like another rearrangement of the 3/2 times pressure times volume. But like, I guess you can use it. But you gotta be careful. This N is number of gas particles. All right, so if you remember from chemistry, the number of gas particles is the number of moles times Avogadro's number. This V is volume, and this little v is like the average velocity of your particles. Don't think you'll ever see this one, but it's there. So hopefully you can use these equations to answer some of the homework questions and do well on the final exam.